handy example of an application of cross product is finding the distance between two skew lines. So I'm going to be calculating the shortest distance between this line, which starts here and travels along that direction vector, and this line, which starts there and travels along that direction vector. Now I'm going to attempt and fail to draw this correctly so that you can see what we're up to. So this first one, line 1, is going off through space, like so. And line 2 is going off through space, like so, in a manner so that they don't cross each other. So this is like looking at a highway bridge, right? You have one ramp going this way and one ramp going that way. So they get close, but not quite. Now these two lines at some place have a point where they are closest. Perhaps it's there. So the idea here is I need to find this vector that connects the closest point to, on each line. I need to identify the coordinates of this point and this point. And then I need to get the magnitude of this vector to find out the separation. So the catch is that just like finding the distance from a dot to a line, the path of shortest travel is perpendicular to both of those lines. So you have to sort of visualize that. So if I make note of that, the shortest path is perpendicular to both lines. We're going to use cross product in order to find that vector, or something that is at least in that direction. Shortest path is perpendicular to both lines. So we're going to have to look at these lines here and decide which piece is making them go in any particular direction. And that's this part back here. This thing with the letter attached to it is what determines the direction of the line. So if this is true, that the shortest path is perpendicular to both lines, and these are the pieces of those lines that determine their direction, then this path has to be perpendicular to both -6, 2, 1 and 3, 4, -3. So I'm going to need a vector, a third vector, that is perpendicular to both of these, and that is the purpose of cross product, is to take two inputs and generate a third vector that is perpendicular to both. So once I have that, I'm going to do some an example that's very similar to the distance from a dot to a line. I'm going to get that cross product done first, so that, and then I'll clear up some space so we can go from there. So to do my cross products, I will have to take this first one, -6, 2, 1, those are my x, my y, my z, and then 3, 4, -3. And just like in the last example, I'm going to take this x column and I'm going to duplicate it at the back just for convenience, so that when I go to do this cross product, to get my x values, I do y times z minus y times z, 4 times 1. To get my y, it would be 1 times 3 minus -3 times -6. And to get my z, I would use these two columns. It would be -6 times 4, subtract 3 times 2. All right, so 2 and a -3 is -6. 4 times 1 is 4. 1 times 3 is 3. Minus -3 times a -6 is a positive 18. -6 times 4 is -24, and that's subtract 6, which gives me -6, -4 is -10. 3 minus 18 is -15. And minus 24 minus 6 is negative 30. All right, so I have this vector, negative 10, negative 15, negative 30, and if you notice, those are all divisible by negative 5. So I'm going to pull that out. This leaves me with 2, 3, 6. All right, lovely. So now that I've got that done, I'm going to look back at what this means. So I have this vector here that's perpendicular to those two. So this vector here must be parallel to this one. It doesn't have to be this one necessarily, right? Like I've got a coefficient in front here that may or not be correct. And I have some numbers in here. And as long as I'm following the right proportions, I should end up with something that's parallel to that. I'm going to just jot that in here. That path is parallel to negative 5, 2, 3, 6. Okay. So now that I've got this, I'm going to try and construct this vector in two different ways. First off, it's this vector with some parameter on it to stretch it or shrink it. The second way I'm going to construct this vector is to take the coordinates of L1 and subtract the coordinates of L2, right? Like that's how we did a vector from one place to another. So if I can construct this vector by doing this minus this, and I can construct the vector by doing this multiplied by a new letter, I'm going to use m, then I should be able to equate them. And what it will end up creating is 3 equations in 3 variables that I can solve using substitution and elimination. So I'm gonna write this thing up here so we can remember it. Let's use negative 5, 2, 3, 6, m will be this vector connecting the two lines. So I'm going to clear this off, and then we're going to create the vector by doing subtractions and see what we get. All right, the second way that I can construct this vector here, connecting my two skew lines, is to take the coordinates of line 1 and subtract the coordinates of line 2. So if I do that, negative 11 subtract negative 9 would be negative 2. 7 subtract negative 21 would be 28. 5 subtract 2 would be 3. And then I have p negative 6, 2, 1 subtract q 3, 4, negative 3. So if I gather that all up, this vector here connecting the two lines should be negative 2 minus 6p minus 3q. 28 plus 2p minus 4q and 3 plus 1p plus 3q. All right. So I've built this connecting vector two ways. I found the vector that is perpendicular to both the direction vectors, and I said it's some multiple of that thing. I don't know, maybe it's twice this, maybe it's half this, maybe it's 3 times that, I don't know. That's one way of constructing it. The second way is to construct it by going coordinate by coordinate and subtracting each thing, and so I've generated it like that. The way I'm going to finish this is to say that this vector here, this construction, has to be equal to that construction, right? They're both the same line. They're both the thing that connects our two skew lines through 3 dimensions. So this representation must match that one. So I'm going to erase this because I'm going to need a lot of space, and I'm going to actually connect those things. Alright, so if I look at this vector, if I equate this to this, then my x-coordinates of this version have to match my x-coordinates of that one. So -2 minus 6p minus 3q has to match -5 times 2 is -10 m's. If I equate the y's, then 28 plus 2p minus 4q's has to be equal to -5 times 3 is -15 m's. And if I equate the z's, 3 plus 1p plus 3q has to equal -5 times 6 is -30 m's. Alright, so now that that's done, I'm going to clear this out of the way, and we're going to have to do a massive exercise in substitution elimination. So right now I have 3 equations and I have 3 variables, and that's just enough to come up with a single solution. So how am I going to do this? Well, first I'm going to notice that 3 of these would match my m's. Right, I would have 30 m's here and 30 m's there. So I'm going to do that. This equation times 3 would be -6 -18p minus 9q equals -30m. And this equation here, I'm just going to write it underneath. And I'm going to do some subtraction here. So -6 minus 3 would be -9. -18 minus 1 would be -19. -9 minus 3 would be -12. And -30 m's minus -30 m's is gone. Now that was the whole point, is that I took 2 equations and I used some scaling up to eliminate one of my variables. I'm going to do that again, combining these 2 equations instead of these 2 equations, and then I'm going to have another thing with a p and a q in it. Once I have that, I'm going to use this equation with a p and a q and this equation with a p and a q to eliminate one of those variables, and I'll get it to say p equals this. So that's the process. So the next thing I'm going to do then is to look at these 2 equations, so I can eliminate m again. If I double this, I'd have a match, so I'm going to do that. Double this one, I would have 56 plus 4p minus 8q equals -30m. 8. Good. And I'm going to write this one again. 3 plus 1p plus 3q equals -30. And 56 minus 3 would be 53. 4 minus 1 would be 3 p's. -8 minus 3 would be -11 q's. And these are gone. Okay. Good. So I'm going to choose one of these things to get rid of. I think I'm going to isolate q and use it to scale up. So if I pulled this 12q over, I would get -9 minus 19p equals 12q. And if I pull this over, I would have 53 plus 3p equals 11q. So to get a match there, I could make this match this if I multiplied everything here by 11 and I multiplied everything here by 12. because 12 Qs times 11 will be 132 Qs, and 11 Qs times 12 will be 132 Qs. So it's like doing a common denominator with fractions, right? I'm just finding a way to scale these things up properly. So fetching my calculator, negative 9 times 11 is negative 99, and negative 19 times 11 is negative 209. 53 times 12, 636, and 3 times 12 is 36 P's. So if this is worth 132 Qs and this is worth 132 Qs, then this thing, negative 99 minus 209p, should be equal to this thing. So I'm going to kick the 636 over there and the 209 over here. P plus 209p. That will be negative 735. This is 236, 245 p. And so to finish, negative 735 divided by 245 is p. So you pull out your calculator, 735 divided by 245 equals, well, exactly negative 3. Isn't that tidy? That's not necessary, or it's not necessary that it be clean. I have tried to engineer some of the practice problems to come out tidy, and I certainly engineered this one to come out tidy as our first example. But it is nice when you just get a nice clean number like that. So now what? Well, I have P, I need Q, and I need M. Fortunately, now that I've done all this mess, all I have to do is find an equation that has just a P and a Q in it, and I can substitute this value and calculate from there. So I'm going to go with this one, just because it looks pretty tidy. I'm going to do it over here. So 53 plus 3p is going to give me 11 Qs. So I already know p is worth negative 3, so it goes in here. Three times negative 3 is negative 9. 53 minus 9 is 44, and 44 over 11 is 4. So again, that's nice, it's tidy. Now that I have a Q and a P, I just need to get an M value. This looks like a nice tidy place to get it from. So minus 2 minus 6p minus 3q equals negative 10m. I just grabbed this equation up here. I know that p is worth negative 3 and q is worth 4. That's negative 10m. So negative 2 minus 6 times negative 3 is plus 18. Negative 3 times 4 is negative 12. Negative 2 plus 18 would be 16. 16 minus 2 is 4. Is that right? Yep. 4 divided by negative 10 is m. Therefore, m is negative, is that 2/5? All right. Goodness. So what does that tell us? Well, I'm going to erase everything except these three numbers at the bottom. We're going to bring back the original lines we started with, and we'll try and figure out what we've just figured out. So we started this problem with an equation for line 1, an equation for line 2, and then we calculated this vector that connects the two of them at the shortest point. And it had, of course, an m at the back. There we go. So after a whole bunch of algebra, I figured out that the value of q was 4. Well, q is there. The value of p is -3, and that's here. And the value of m is -2/5, and that's up there. So all I'm going to do is to take these numbers and fill them in and see what I get as a result. So L1 would be -11, 7, 5 plus -3 times -6, 2, 1. And then I'd have L2 is -9, -21, 2. Q is 4. Times 3, 4, -3. And D is -5, 2, 3, 6. And my M value is -2/5. Okay, so I'm just going to go through and I'm actually going to work out all the additions and scalar multiplications here and see what we have. So L1 then is -11, 7, 5 plus -3 times -6 is 18. -3 times 2 is -6, and -3 times 1 is -3. -11 and 18 would be 7. 7 and -6 would be 1. 5 and -3 would be 2. So I've got that. In my next one, I have L2 is -9, -21, 2 plus 4 times 3 is 12. 4 and 4 is 16. 4 and -3 is -12. So L2 is at -9 and 12 would be 3. -21 and 16 would be -5. 2 and -12 would be -10. And back here, D would be, well, -5 times -2/5 leaves that as just a factor of 2. So D should be 2 times 2 is 4, 2 times 3 is 6, 2 times 6 is 12. All right. So what we've got here is a point on L1, and we have a point on L2, and we have this vector that connects the two of them. And so again, you can look, 3 plus 4 would be 7, -5 and 6 would be 1, -10 and 12 would be 2. So this vector does in fact connect this dot to that dot. So what do these all mean? Well, if you leave here, leave L2 here, and arrive at L1 here, you will have traveled along this vector, which is the shortest distance. You will have done so on the shortest path. And that's what we were asked to do in the first place, was find the distance between these two skew lines at the closest point. So the only thing I don't have is what that actual distance is. Well, all I need then is the magnitude of this particular vector. So the magnitude of D is the square root of its x coordinate squared plus its y coordinate squared plus its z coordinate squared. 4 squared would be 16, 6 squared is 36, and 12 squared is 144. 16 and 36 would be 40, would be 52, plus 144. 52 and 144 was 196. I'm pretty sure the square root of 196 is 14. Just check that for you. Indeed. So, therefore, the two lines are 14 units apart at their closest approach. All right, so you took these two skew lines, and skew just means they don't cross. Maybe we should have led with that. You took these two lines that don't cross each other, and you defined them using a point where they start and then the direction they travel in. And you were able to find the vector that's perpendicular to both, and then use substitution elimination to work out exactly where you leave this line and where you arrive on this line to travel the shortest path, which you defined as a vector and then could calculate the distance of. And that was a lot of work, but if you, again, think about what you just pulled off, right? Like, this is a totally abstract line in 3 dimensions, and so is this. And despite them being something that you can't draw and you can't build, really, not effectively, you still managed to find out the minimum distance between those two pathways through space and calculate the exact distance there. Like, that's really profound and very powerful. Just as a quick example, if you think about something like the Earth going around and around and around the sun, and you have something like Mars going around and around and around the sun, if you're trying to get from Earth to Mars, you have to be able to abstractly represent where the orbits of those two planets are, so that when you launch your ship, it can actually intersect with where Mars is going to be once the ship arrives there. So being able to do this, right, to describe a path in abstract and then use algebra in order to calculate the shortest distance or where you leave and where you end up, that's very powerful and very necessary for doing very large or very small scale operations, right? Things where you can't actually sit down and measure with a tape measure or a protractor. So whether you're dealing with planets and stars, or if you're dealing with individual molecules, etc., inside of DNA strands or what have you, being able to represent and model their paths or where they are or where they're going in abstract, and then use that model to deduce things like separations or travel times, allows you to get away with lots of dirty stuff in engineering.